Dear students, in this video we are going to discuss about rectangular components of torque. We have studied that torque is the rotational effect of the force. Whenever a force applied on the body tries to rotate the body, then we say that the torque has been produced. And torque is given by tau vector equals to r vector cross f vector. Right? This video is in continuation with the previous videos on torque, whose link I have shared in the description. So you better have a well guided description on torque, and then only we'll see this rectangular components of torque. So tau vector is written as, in the component form, it is written as tau x I cap, tau y j cap, tau z k cap, where all of them are the components of torque. Similarly, r vector can be written as xi cap plus yj cap plus zk cap, and f vector can be written as fxi cap, fyj cap, fzk cap. See, all the quantities involved in this expression are vector quantities: tau vector, r vector, f vector. So, all these vector quantities can be written in the component form, and component form is nothing but I cap, j cap and k cap, right? So now what we need to do, this term is written as it is, this LHS is written as it is, and we have to do the cross product of these two quantities. So how can we do that? See, cross product follows cyclic order: I cap, j cap, k cap. Okay, so I cross j will give you k, j cross k will give you I. Similarly, k cross I will give you j cap. So this way, by following this cyclic order, we can find out the cross product, right? So we need to cross product the terms sequentially, like xi cap cross product with fxi cap. So xfx I cross I, which is 0. Reason being, because a vector cross b vector means magnitude of a, magnitude of b, and sine theta and sine 0 degrees. See, I cross I means same vectors. So same vectors will have an angle of 0 degree with between each other. So sine 0 degree is 0. So this way we can do the cross products, and once we are over with the cross products, we are left with this stuff. So combine the terms containing I cap, j cap and k cap. Once you combine the terms, what are you going to get? You are going to get the equation like this. So after that, just see tau x I cap and this stuff of I cap compared here. Comparing the coefficients of I cap on both the sides, j cap on both the sides and k cap on both the sides, we get the value of tau x, tau y and tau z, which are the rectangular components of torque, right? That's what we had talked about, that in this derivation we aimed at finding out the rectangular components of torque, and the rectangular components are tau x, tau y and tau z. After that, we'll be finding out angular momentum. So we know that rotational effect of force is known as torque, and force is equal to dp by dt. It is equal to rate of change of linear momentum. That's what we know. So if in linear motion, force plays the role of displacing a body, similarly in rotational motion, torque plays the role of rotating a body, of displacing a body circularly. So if force and torque are analogous to each other, like in linear motion you get the help of force, and in rotational motion torque is the same thing as force is in linear motion, right? So torque will also be the derivative of some kind of quantity which will be known as the momentum associated with circular motion. Like this is the momentum associated with linear motion. So there must be some momentum associated with circular motion, and torque will be the derivative of that. So we will find out this in this derivation, that just like in linear motion, we know that the linear force is the derivative of linear momentum. So is the rotational force, which is known as torque, is the rotational force called torque also the derivative of some quantity which will be known as the momentum associated with rotational motion? So we aim to find it, right? And to begin with, we know that in Cartesian coordinates, torque has the expression xfy minus yfx, right? So this is the expression for torque in Cartesian coordinates. Okay, so talking about fx, and then we'll talk about fy. So fx, which is the linear motion, this is the linear force, the force associated with linear motion. This is equal to dpx by dt, the derivative of momentum, right? D by dt will remain as it is, and in place of px, we'll write mvx, right? Mass into velocity, because linear momentum is nothing but mass into velocity. So anyway, mass can be taken constant out of the differentiation, and what are we getting? Dvx by dt. Same way, Fy, which is, the force in y direction, that Fy is equal to dpy by dt, right? So d by dt remains as it is. In place of py, we can write mvy, mass into velocity, because this is linear momentum, and mass can again be taken out of differentiation, and you get dvy by dt. So these are the values of fx and fy which undoubtedly you can put in this expression, right? So here in this derivation, we are aiming to prove that torque is also the derivative of some quantity which will be later on known as angular momentum. So once you put the values of fx and fy in the expression of torque, you get this. Take mass constant outside and you get this. So now we encounter a problem here, that force was coming out the derivative of linear momentum. So we want a form like this only for torque. Actually, you know what we are trying to prove? That torque is an analogous to force. Like what role force plays in linear motion, the same role torque plays in rotational motion. Like what role force plays in linear motion? If there's an object, you apply the force and the object moves. So force plays a role of displacing an object or stopping a moving object in linear motion. So torque plays the same role in rotational motion. It helps the body to rotate around a particular axis, right? So if force is the derivative d by dt of some quantity, so torque should also be the d by dt of some quantity, because both of them are playing the same role in their respective fields, right? So but here what we are seeing, that torque is not directly coming as the derivative of something. It's a complex form. We are not getting a form like as simple as like this, right? So how can we go about it? First of all, let's do d by dt of xvy minus yvx. We have got a form like this, no? So just see, if d by dt of xvy minus yvx, what is it? So this will be d by dt of this quantity minus d by dt of this quantity, right? Now this is u into v. U into v means product rule. So keep this quantity constant, take the derivative of the second one, plus keep this quantity constant and take the derivative of the first one. Now minus sign, same rule. This is UV rule, product rule. Two quantities are getting multiplied and you have to differentiate them, right? So keep the first one as it is, take the derivative of second, plus keep the second one as it is, take the derivative of first. It's as simple as that. So after that, you get dx by dt. Dx by dt means the derivative of x coordinate with respect to time, right? So that will be velocity vx. Same way, dy by dt will be the derivative of y coordinate with respect to time. So that will be vy. Velocity is displacement per unit time only. So vx vy plus and minus, they cancel each other. So you get this. You know what I have proven by this? That this stuff is numerically equal to this stuff, right? So this stuff is nothing but this quantity. So in place of this quantity, you can of course write this. So you can write m d by dt of xvy minus yvx. So once you write it, take mass inside. Reason being, mass is a constant. It can be taken outside or inside the differentiation. So now you have reached this form finally, that torque is coming out as the d by dt of some quantity. Earlier it was not coming like this. Torque was not directly coming as d by dt of some quantity. It was having derivatives, but derivatives were involved in the perplexed form inside this expression. But here torque is directly coming as the d by dt of some quantity. And let us name this quantity as L, where L is equal to this stuff. Now this L has taken place of P. P used to be there, dp by dt. P used to be there in linear motion and L is there in rotational motion. So L is nothing but angular momentum. P was linear momentum. So this is indeed a quantity which is the rotational analog of linear momentum, and this is called angular momentum.